Welcome to Novinium's Masters of Reliability webinar series. Today's topic, regulatory approval of aging utility cable infrastructure programs. My name is Chrissy, and I'll be your moderator for today's session. If you have questions at any time during the webinar, please feel free to enter them into the chat window, and we will address them at the end of the presentation. This webinar will be recorded and available afterward at novinium.com. Joining us today is our expert guest speaker, Dr. Richard Brown. Dr. Brown is the Principal Engineer and Director of the Engineering Management Consulting practice at Exponent. Dr. Brown has published more than 90 peer-reviewed technical papers and has written 2 books, Electric Power Distribution Reliability and Business Essentials for Utility Engineers. He earned his PhD from the University of Washington in Seattle and his MBA from the University of North Carolina in Chapel Hill. He is a fellow of the IEEE and a registered professional engineer. Richard, welcome, and I now turn the presentation over to you.
Okay, thank you, and thank you everybody for joining. I am, in about the next hour, I want to talk about this topic of aging infrastructure, but specifically how it relates to regulatory rate case recovery. So that if you decide to tackle aging infrastructure, you can try to minimize the potential troubles that you're going to get there. For those that aren't familiar with my company, Exponent, we're just a large consulting company that does science and engineering consulting, about 1,000 people based in Menlo Park, south of San Francisco. This is what we're going to cover today. We're going to go over just generally rate cases, so that people that aren't familiar with the rate case process get an understanding of this beast. Then talk about aging infrastructure and component failure rate modeling and population aging. Talk about proactive replacement programs and rejuvenation programs within utilities and how these need to be treated a little bit different than typical types of spending programs within utilities, and then we'll go into a case study and see how all of the things that we covered in the first 3 topics came together in this aging infrastructure program at a U.S. utility, and then just a little bit about commission and commission staff engagement before we finish. And it should take a little bit under an hour, hopefully, to do this, and then we can open up for questions, as has been mentioned. So first, let's get an idea of who is on the phone here. So a poll window will pop up, and just let me know what type of company is your employer, please.
I'll give everyone a few seconds to answer this question. And I'll be closing the poll.
Okay, so very heavy on the utility side. So all of this is near and dear to your heart, and then sort of a mix of others. So that's always like to speak directly to the utility audience. So that is good for this presentation. You are the target I had in mind when I put it together. I need to get. Okay, so now the first topic I wanted to cover was rate cases, and I'm going to, this presentation will be available, and so I'm going to go through it a little bit quickly, but the slides will be available for you for reference. But the point here is that rate cases are basically when utilities are trying to get recovery for the spending that they're achieving. And when you're talking about capital spending, historically, most utility capital spending has been for capacity additions, like a new power plant or a new transmission line, circuit extensions, new substations. All of these were built because you needed new capacity, which means that people were using more electricity, which means that you had naturally more revenue. So these capacity spends were associated with essentially increases in energy consumption, therefore not necessarily resulting in an increase in rates. This is different for equipment replacement and equipment equipment rejuvenation programs, because now you're spending money, but there is no associated increase in energy usage with this spend, meaning that rates need to go up to pay for these programs generally, and so they aren't necessarily as easy to get through the rate-making process as spending categories that don't result in upward rate pressure. First thing for people who aren't aware that is done in a rate case is determine what's called a revenue requirement. This is the amount of money the utility, for the most part, needs to earn over a year so that they can be financially healthy. And there's really two components. There's the expense component, which is how much you're spending for operations and maintenance, and then there's your income taxes and depreciation expense. The other category is based on all of your things that are capitalized on your balance sheets and are in what's called your rate base. So that last line should actually be, say, rate base times rate of return. And this is really a proxy for how much investors need to be compensated for loaning you money in terms of equity financing or debt financing. And so that is what's called your revenue requirement. Now, after your revenue requirement is determined, then you need to determine how you're going to earn that revenue requirement in terms of rate design. When you are designing rates, which is, okay, we need this revenue, but how are we going to get this revenue in terms of residential rates, commercial rates, industrial rates? What are the regulators considering here? And I just want to highlight a couple. Of course, the utility wants enough money to be financially healthy to be able to do what it needs to do. But the regulators historically have focused on cost of service. We just want the rates to reflect the cost of service of the utility. Increasingly, though, there has been focus on other aspects, such as changes in rates should occur gradually, no rate shock, and consistent with public policy goals, such as we don't want to discourage new businesses from locating in our service territory due to high electricity rates. And so these concerns that regulators are increasingly considering all tend to push back against types of utility spending that potentially can result in rate increases. These are the general steps that occur during a rate case. After you determine your revenue requirement, you need to justify the costs that are associated with that revenue requirement, the so-called prudency test, come up with rate structures, and then come up with this rate of return number. This is an expanded form here of the rate case process. Notice it's very complicated and long. And it is not possible in a complicated process like this to look at every single line item of utility spend. And so just be aware that, say, an aging infrastructure program may not be debated at all in this process, but when the final commission order comes through, it could very well be disallowed. Or conversely, if you do a good job of presenting and justifying your aging infrastructure spend, it also could maybe not be debated at all, and at the end, it is approved. But just be aware that just because it's not addressed in detail in this process is no guarantee that it is going to be approved in this process. It's very easy for decisions to be made that aren't really linked back to the debate and the evidence that were presented in this process. You want to do all you can to make sure that what you're proposing is a non-issue in this rate case process. Two ways really of going through a rate case process, and this is going to depend on which state you are in. It varies by state. The most common is called a historical test year. This is where you take the financials of an actual fiscal year of your utility. How much energy was used by different categories of customers during this year? What were our actual expenses during this year? And based on these actual expenses, what do we need our revenue to be, and how do we need to change our rates so that we could have achieved that revenue? You don't get a big circus in this process, but there are some challenges with spending money in different ways. One is what's called regulatory lag, and that is if you weren't spending money on aging infrastructure before, that's not in your current rates, and you're not going to be able to get recovery until you start spending that money before you go into a rate case. And so you have to take a bit of a leap of faith to start spending this money. And then, of course, when you start spending this money, you have to go through the entire rate case process, and that may or may not get approved. And so this particular historical test year really makes it risky to spend large amounts of money in ways that are different than how you've spent in the past. Second category is called a forecasted test year. This is when the utility would go to the regulator and propose what they intend to spend in the next, say, 3 years. Of course, in this case, you can propose, we weren't spending money on aging infrastructure. Now we want to spend money on aging infrastructure, and it will either be approved or not approved. Of course, if it's not approved, then you're not going to do it, but you're not addressing the aging infrastructure problem. Also, everybody comes out of the woodwork. And the people that come out of the woodwork are the people generally that don't want the utilities to spend another penny more than they have to. So they're going to challenge your assumptions, challenge your benefits, challenge your motivation, and just generally try to make the utility look bad. And so a forecasted test year has problems of its own. So just a question for you, for the utility people here, in terms of your rate case situation. I'm just curious how much of you have recently gone through a rate case or planning to go through a rate case in the next few years.
I'll give everyone a few seconds to answer this question. And I will be closing the poll.
Okay, so we have about 85% of utilities over a 6-year period had some sort of or expect some sort of a rate case activity. And this is consistent with what I've seen through the broader industry. You know, years past, in the 70s, very common for utilities to have rate cases every year, and then there was a period starting in maybe the early 1980s where many utilities went for 15, even 20 years without a rate case. Now they are becoming more common, and as your utility starts going through more regular rate cases, it's going to be easier to start gradually ramping up in different categories of spend, like aging infrastructure replacement, aging infrastructure rejuvenation. So we can go back to the slides. Okay, and so here is just a summary of some of these risks. Historical test year, they can deem your spending imprudent and just disallow that spending, then the utility has to eat it. They can reduce your rate of return. So effectively they're saying we're not going to disallow it, but we're going to reduce your rate of return, so effectively rates don't have to increase. And they can also phase in rate increases to avoid rate shock, and of course that means that you don't really get as much recovery as you would have if rates were fully phased in the early years. And then we talked about the forecasted test year risks. And then the last one is something that everybody should really be aware of. Utilities are basically going to be accused, if you're spending large amounts of money on areas like this, of trying to just shore up your rate base, trying to finding ways to satisfy investors by increasing revenue and earnings, and basically accusing utilities of being greedy. So it's just it's the life that you live. And so just be aware of it and be prepared for it. So that's the rate case, aspect of things. Now let's just talk about the aging infrastructure aspects of things. You know, you have real equipment in the utility that's needed to provide services to your customers, and every year a piece of equipment gets a year older. Why do we care? Why do we care about equipment aging? Generally, it's because it tends to fail more often. So failure tends to increase with age for most categories of equipment that utilities use. So that's going to be a safety issue. It's going to be a reliability issue. Also, maintenance costs can tend to increase as failure rates increase, and you have to address this with reactive maintenance. For certain types of equipment, really old circuit breakers or something, you may not be able to find replacement parts anymore. So you have to machine your own replacement parts, and then you may have technical obsolescence as well. Let's just, you see the pictures over here to the right where you have a wood pole and then you have a pole that's been braced. So here's a scenario for you. Say you have a wooden pole that is otherwise healthy, but it has some deterioration at the ground line, which reduces its strength. And you have two options. You can replace that old pole with a brand new pole, or you could just put a steel brace at the ground line, which restores the strength at the ground line, but you still have that older pole. So let's have people tell me what the preference is. Replace the pole or brace the ground line of the pole.
All right, I'll give everyone a few seconds to answer here. And I will be closing the poll.
Okay, we got a lot of utility people on the phone. Yeah, generally, you know, the utility mentality is why do we want sort of a, you know, half-baked solution or an ugly solution or a Band-Aid solution when we can just get a brand new piece of equipment in there. And yeah, I kind of get it, but there's budget constraints in a lot of utilities these days, and so you can't necessarily you know, spend as much money as you want. And so I would just say, think about, say you had 100 poles that needed to be addressed, and you only had the budget to either brace all 100 of them or replace 30 of them. Would you rather have 30 new poles and 70 poles that were unaddressed, or 100 poles that were that weakened portion was addressed on all 100? And so in an age where you had as much money as you want and nobody pushed back on budgets, yeah, so put in the new stuff, sort of the gold-plated solution. But that's not always feasible, you know, in the budget situations that utilities have today. A little bit of a different flavor, but we talked about underground. Let's go to the slides. Let's talk about, instead of overhead, underground. So say you have a subdivision that has some cable in there, and it was all put in at the same time, and you're starting to see, you know, these sections fail more often. And so there's a couple ways to address this. One would be to replace all this older vintage cable with new cable, and the other would be to inject the cable. So sort of restore the insulation strength of the existing insulation without replacing it with new cable. So let's open that up for a poll for preference.
All right, I'll give everyone a few seconds to answer here. And just a few more seconds. All right, I'll be closing the poll.
Okay, we might have a little bit of a selection bias based on who called into the Novinium seminar, but it's a little bit more even here. I guess the reason why I put this in here is a lot of utilities that I've talked to look at injection as really a niche application. If we have cable that would really be disruptive to have to replace, or really expensive to have to replace, then in those situations we're going to look at injection as an option. Otherwise, our preferred is replacement. Whereas my scenario I gave you was just more comparing apples to apples solutions, addressing something that you could easily replace it if you wanted to, but why would you replace rather than injecting if injecting was a lower cost solution? So same sort of flavor here, but it seems like maybe it's just because you don't have to see an ugly steel brace. The injection doesn't have any visual impact, but it does seem like the utilities here are more open to using a less expensive alternative to address the issue rather than spending as much money on replacement. So we can go ahead and move on to the slides. So if you're going to address rigorously the issue of aging infrastructure, you need to know what you've got in terms of age, population age. And this is just an example of data from a utility and in terms of how old their cable is. And each square is just how much, in this case, what percentage of cable is exactly that year old. And then the solid line is the percentage of cable that is that many years or older. So you can see for this particular cable, for this particular utility, about 20% of their cable is 30 years and older. And this is just sort of an example of the type of data that you would want to have if you're going to address aging infrastructure. Here is an example of 5 different utilities. I got this data about 10 years ago, so it's a little bit old, but in this case, at least 10 years ago, if you think of 30 years as sort of the expected life of underground equipment, you have one utility over here that has pretty young population, but the other 4 utilities, 2 of them have about 20% of their cable that's older than 30 years, and you have a few utilities, 2 of them, where about a third of their cable is 30 years or older. And again, this was about 10 years ago, so now you could expect that these curves have shifted about, roughly 10 years older than they are now. So, some utilities, a third of their cable is 40 years or older. So, question just for the utility employees now, do you have this type of data for your, and we'll restrict this to cables right now.
We'll give everyone a few seconds for this poll. And just a few more seconds. All right, I'll be closing the poll.
Okay, so here you're in a situation where some of the utilities don't really have good cable data. Some think they have most of this data, about a third and about half, just sort of. I'll say you probably have better data than you think you have, and you can back into a lot of this data going back through accounting records. And so, if you're thinking, oh, is this data in our geographic information system or something like that, and that's where these numbers are coming from, you may have better data that you think if you're willing to work for it. Okay, slides. So, what actually happens to a population age as time progresses? And this is just an example here. Say you installed a bunch of equipment at year 0 when it was all new, and this equipment had a low failure rate for the first 30 years, and then after 30 years the failure rate started to ramp up linearly. What is going to happen to the average population age? You can see in the first 30 years the average population age tends to increase almost linearly because the failure rate is low, so every year your average age is a year older. But as failure rates start to increase at age 30, you see you're replacing old cable with new cable, and your population age actually self-rejuvenates. So, to a certain extent, aging infrastructure is a self-correcting phenomenon. The question, though, is just how many failures are you willing to tolerate on your system for various reasons. This is average age. When you're looking at aging infrastructure, oftentimes you don't want to look at average age. You want to know what percentage of really old stuff we have. And so this would just be an example of amount of equipment that is older than, in this case, we use 30 years. So, of course, if you install all your equipment at year 0, none of it's older than 30 years until you hit that 30-year mark. You have this big spike, and then that old equipment starts getting replaced as it fails, and then you sort of have an oscillation. We're talking long time frames here, but this just gives you an example of what would happen if you just had a replace when fail strategy in terms of population of very old cable. Oftentimes, the best way to justify aging infrastructure is, especially on the distribution system, would be the impact to reliability. So this is an example here of what would happen with SAIDI, which is the System Average Iteration Duration Index, basically the average customer interruptions of minute per year. If you started at a 100 for all causes, and you were looking at the SAIDI increase just due to increasing cable failure rates, you can see in this example, as failure rates increase exponentially, even as you have a self-rejuvenating system, SAIDI is going to go from a base of about 100, a starting point of 100, to almost about 120, almost a 20-minute increase before things start getting better with the replace to fail strategy. So if you're able to communicate this internally and to regulators as to why we care, this is a good example of why we care, because of all of the regulators understand distribution reliability indices now and their importance. So we are interested in coming up with failure rate models for cables. To do this, we need to understand what are the characteristics of the cables that actually fail. So when you have a cable that fails in the field and there is an outage ticket or some record work order or something, what information for the utility employees is collected when a cable actually fails? We'll send that out to a poll.
Give everyone a few seconds to answer this. Please select all that apply. And just a few more seconds. All right, I'll be closing the poll.
Okay, so this is interesting. So we have some utilities that don't collect any of this data. I would suggest that you start. And then in terms of rated voltage, insulation type, and conductor type, a lot of times, and I don't know the thinking of the poll takers, but you can get this information based on where the failure happened from circuit information. So you can usually get this information. But of course, if you're going to come up with age-based failure rates, the most critical thing to capture is age itself. But you're not going to necessarily have this in your circuit models unless you have this information like in a geographic information system. You can actually do this in a separate process as well, especially if you're a medium or large-size utility. You can just have a special program for a few years where every time there is a cable failure, you just have somebody go and collect information about this. And after you get about 3 or 4 years worth of data, you will have enough information to be able to come up with pretty good failure rate models, even if it's outside your normal outage management process. Go to the slides. So within a utility, in addition to the rate case issues, there are sometimes obstacles within utilities to tackle aging infrastructure. I always joked how you start explaining aging infrastructure problems and what it's going to take to executives, and they're interested at first, but by the end of the conversation they're like, no, let's not address this, and I hope I'm retired by the time the problem gets too bad. So you can only kick the can down the road so far, though. So what I want to talk about briefly, and I'm going to go through this somewhat quickly, is just traditional utility budgeting and why this sometimes is not compatible with aging infrastructure. And it is, there's a couple different categories of spending in utilities. One is capital spending, or CapEx, and the other is operations and maintenance spending, or OpEx. And I'll explain to you a little bit the challenges. There are challenges with each, but there are different challenges. So expense budget. For the accountants among you, it's pretty simple to understand that your profits, or your earnings, are equal to the revenue that you achieve minus the expenses that you have. Profit equals revenue minus expenses. Shuffle around the equation, and you have an expense budget. The expenses that you can afford to spend are equal to your revenue minus your earnings target, how much profits your executives have communicated to the investment community. So it's pretty simple. This is how much money you have to spend. And if you have a mild summer and revenue is a little bit lower, you all know what happens to your expense budget. It gets slashed. You are not going to spend more than this equation, or at least there's going to be very serious pushback. And the opposite is also true. If you have a really hot summer, revenue is higher than expected, you're going to get pressure to spend more money, so that at the end of the year, the regulators can't accuse you of earning too much money. So that is the constraint here. More than that, though, the utility budgeting process this year is usually based on all of the expense budgets from last year. So if you want to address an aging infrastructure problem with some sort of a expense option, you're going to have to basically take away from other existing expense budgets. Not so easy to do, at least for most of the utilities that I've seen. Now, capital spending is a little bit different, because when you spend money on capital now, it doesn't hit earnings now. It hits earnings as that asset is depreciated over its useful life. So you can spend money on capital today without really violating these earning targets. The problem with CapEx spending, though, is you do need cash for these expenditures, and so increases in CapEx spending would mean that you would need to issue more debt and or more capital, which utilities are not averse to doing as long as they're pretty convinced that they're going to get rate recovery for this capital expenditure. So just question. And everybody can answer this one, but if you could spend $1 of capital or spend $1 of OpEx, what do you think utilities prefer to spend?
All right, just a few seconds for this question. And I'll be closing the poll.
All right, very nice. Okay, so yes, I tend to agree, but maybe it's a little bit more nuanced based on what I explained. It's not that you don't want to spend OpEx, it's that you want to hit your OpEx target so that you can hit your revenue target, and then CapEx that can be justified and recovered through rates would be preferred for incremental spending for the reasons that I stated. But certainly for an aging infrastructure program, it makes sense to address this with CapEx. That's going to be easier for internal utility process for sure, That would be both like equipment replacement and capitalizable maintenance, such as cable rejuvenation. I think most states allow this type of approach to be capitalized, where you're extending the useful life outside of normal maintenance practices. That type of activity is typically capitalizable within the utility. Okay, slides. Okay, so this is, again, the capital budget here. This is just comes from the cash flow sheet. We're going to not spend time on that slide. So this is what you need to ask yourself, because you will be asked this, because utilities are budget constrained. Everybody's always asking for more money every year, all the time, and there's not enough money to go around. And so oftentimes there will be a response when anybody's proposing a program or an increase in a program is this. Okay, I agree that something needs to be done, but why does it need to be done today? Why can't we just defer this spending by 1 year? And that is if you don't have a good answer to this question, it's a really good way for your proposal to be not approved, to be deferred, and next year you get this same question asked, and the same question asked, and the same question asked. And so another approach needs to be taken rather than just looking at year-ahead budgets and the impact of the system in the following year if you want to tackle the aging infrastructure problem. And I will address this issue by going through a case study. So a little background, this is a California utility, and the California utilities are under a prospective rate case program. So they have a forecasted test year. There's 3 major utilities in California, and each of them goes through a general rate case in rotating years. So one utility decided to go in and weren't spending money proactively on aging infrastructure and proposed a lot of spending in some different categories of equipment on addressing aging infrastructure, and 100% of it got disallowed. No success at all in getting the regulators to approve aging infrastructure spend. So this utility, who's the subject of the case study, looked at that and said, well, hey, we think we really need to start spending money here. However, we don't want that to happen to us. So what can we do to make sure that our aging infrastructure proposal gets approved, unlike what happened with the utility last year? So this is the general technical process that went through the analysis, what was called a feature analysis. How are we going to categorize the cables based on feature? How are we going to come up with failure rate models for all of these? How are we going to look at the impact of our current business as usual on the system as we would age over time? And then let's look at some different proactive replacement and or rejuvenation scenarios so that we can see what different approaches would do to the system impact. Here's just an idea of the scale that we're talking about here. This particular utility had these 3 types of extruded cable in their system. HMWP, that's high molecular weight, polyethylene, sort of older vintage cable in general, and at this utility, cross-linked polyethylene cable. That was sort of a second generation at this utility, and then they had started the last few years of all new cable that they were putting in the ground was a EPR rubber cable. So that would be at this utility, newer vintage cable, and you can see the bulk of it was sort of the second generation cable at this utility. This is an example for one type of cable, the 12 kV cross-linked cable, of what they had in the ground here. And you can see that a significant amount of cable was installed 1975 and before. So you think of today, that's 40 years old. A lot of cable, 40 years or older, that's in the ground. And so This slide right here is just an aggregate of all of their cable that is in the ground. So you can see that they even have cable that's, 1960s, so this would be, over 50, 55 years old. Some really old stuff out there. And you can also look at these types of things to see, are there any sort of waves of really old stuff that are coming our way? If you start to see problems manifest themselves when cables are 35 years, do we have cables that are 30 years old that are in 5 years going to be a problem for us? What initiated that? Somebody at the utility plotted this. They were looking at, and this is paper insulated lead cable, so a little bit different animal from extruded, but they were looking and tracking of how many outages they had on this category of cable. And you see it was holding steady for the longest time at about 10 outages per year. And then starting about 1990, they started seeing a dramatic increase in the number of outages on this type of cable. You see it went from about 10 per year up to about 80 per year, so an 8-fold increase. They're not putting any new paper insulated lead cable in the ground. This is all just existing stuff. And you start having failure rates go up by a factor of 8. That raised the alarm of what's going on here. And is this trend going to continue? Are we going to go from 80 to 200 to 300, or is it going to steady out and stay at 80? 80 is the new normal, or is it going to start going back down? Just we don't know. So we need to try to figure this out. So they decided to look at all of their cable population to make sure they had a good handle on what was going to happen. And the first thing they did was, are there any differences in the different cable categories, just on average, failure rate? And so here you can see in terms of failure rate here, the high molecular weight, remember this was the first generation, the older cable at this utility, had a dramatically higher failure rate than the other categories of cable. So if you're going to start addressing a category of cable, that's a pretty good one to start with. You don't need to dive too deep to see that that should have priority. But we want to get a little bit smarter about it. So what we're going to do is we're going to look at what actually seems to be related to failure rate characteristics. And we're going to do this by what we call a feature analysis. First of all, what are some hypotheses of what may potentially impact failure characteristics? Well, what about main trunk versus lateral? Well, at this utility, main trunk tended to be larger conductor and lateral tended to be smaller conductor. So we looked at all types of cable but separated them large conductor versus small conductor. And was there a difference in failure rate? About 20% difference. So a little bit of an effect, but not a huge effect. What else might affect failure rates? How about voltage difference on our 12 kV part of our system, which would be 15 kV class cable or 25 kV? And here you see a big difference. The 12 kV cable had a much higher failure rate than the 25 kV cable. So we should probably consider rated voltage in our failure rate models. And then the other was, well, what about jacketed versus non-jacketed? Shouldn't the jacketed cable have solved a lot of failure problems? Maybe. We'll test it, and you can see that almost no difference at all for this utility, jacketed versus non-jacketed in terms of failure rate. So that's not really a feature we need to consider here. So based on the feature analysis, 6 categories of cable were selected to develop failure rate models for paper insulated lead cable, the high molecular weight, 2 types of cross-linked, and 2 types of rubber. So failure rate models. We don't really know what a good failure rate would be a priori. And so here are some of the failure rate models that we were going to test to see if they fit the data. Exponential, power model, linear model. We could, of course, test others. So here is some data, and this is just for one of the categories. This was the 25 kV cross-linked. Didn't have a ton of data, but we had enough data to come up with good failure rates for bins of 10 years. So we took failures that occurred on cable that were 0 to 10 years and came up with a failure rate for that, and we plotted that in the middle of the bin at year 5, and that's the triangle right here. Similarly, we took all the failures that occur on cable that was 10 to 20 years old, came up with a failure rate, and plotted that in the middle of the bin at 15. Same thing for the bin 20 to 30 and the bin 30 to 40. And that gives you these 4 data points here. And then we tested fit of the different models to see what fit this failure characteristic. And it turned out to be an exponential model, which is what I would have predicted based on the physics of thermal degradation of cable, but you don't know until you actually get the data. We do only have 4 data points, and so another thing that we did in this analysis is we came up with a confidence envelope. We said, well, reasonably, how good could it be? Reasonably, how bad could it be? And so we're going to do all of our analysis based on this upper and lower bound in addition to our best guess. Once we came up with our model for all of our different 6 categories of cable, we projected out in time on a replace when fail scenario. So the utility right now, you can see, if you just looked at the yellow triangles, which is how many historical cable failures they had, they were around 400 a year. And it maybe looks like you're increasing a little bit, but are you really sure? You don't really know looking at the data that way. But based on these failure rate models, we're actually able to project out our best guess. Does our failure rate models fit our historical data? Looks like it does pretty good. And what would happen in a replace versus failure scenario out in time? And you can see the increases in the total number of cable outages that would occur, and then you have the upper and lower bound. So just to practically think about this, if we have resources right now to address 400 cable failures a year, out in 2020, we're going to be at about 2,400 failures a year, 6 times as many failures. Do you even have enough skilled labor to address that many failures or not? And if not, then you need to start training some personnel or trying to get a handle on this situation in some other way. And this would be projecting it out further. How bad will it eventually get in a replace when failed situation before you would start self-rejuvenating? And in this case, you can see you're over 7,000 failures a year, where you started out with about 400 failures per year before things start getting better. So they're just going to get worse and worse and worse and worse. Pretty compelling story about something needs to be done about this problem. It's not going to fix itself. It's only going to get worse. And oh, by the way, our best case and worst case scenarios, it's just a matter of timing by a few years on how many years you delay the problem or the problem advances. It's not how bad it gets. It's just does it take a few years longer or a few years shorter. What is the implication to reliability? And so for this utility with the failure rate models, we looked at what SAFE is. This is System Average Interruption Frequency Index, or the average number of interruptions per customer per year, and how much of that is due today due to cable failures, and what is going to happen just because of increases in cable failures to SAFE. And you can see that just increasing cable failures is going to increase your SAFE from about 1.1 all the way to about 1.8, which is significant, and regulators aren't going to like that scenario either. So this is using reliability to try to justify aging infrastructure programs. Now we look at the scenarios. A lot of different scenarios were examined. You could examine rejuvenation scenarios, aggressive programs, less aggressive programs, ramping up programs, what have you. In this case, I'm just presenting one of the scenarios that we presented the Commission, which is we're going to replace 2% of our cable per year for 20 years. So after 20 years, we will have replaced 40% of our cable. And we're going to start with the cable that we know is the worst. Some of our identified paper insulated lead cable and some of our high molecular weight stuff. And what will that do to increases in safety and SAIDI compared to the replace when fail scenario? So you can see here a 2% replacement per year. Safety is still going up, but dramatically less than the 1.8 that you would experience with a replace when fail. And then after you know, about 15 years of the program, you actually start improving reliability, and then it steadies off. And so you can present the commission or internally different scenarios and what makes sense, and try to justify your program this way. Now, in this case, and I would recommend this for your utilities, you don't try to justify the entire 20-year program. What you do is you say, we need to look at what is going to happen over 20 years, and we're only going to look at the first 3 years of that program. Then after 3 years, we're going to come back and see if we have new data, new technologies, new price points, to see if we can refine the plan or whether there is some other way to better advance where we want to go. So we're looking out 20 years, but we're only requesting spend for the first short-term component of that long-term aging infrastructure fix. In this case, it was a 20-year forecast and requesting 3 years of funding. And so this utility got this approved. The other part of the story is they said, okay, we also, when we did our analysis, we really wish we had some better data. And so also part of our program is in the next 3 years, we're going to collect this type of data, and we're going to come back to you, and using all that data we collected in 3 years, we're going to come back and we're going to give you a much more even refined program. So data collection was part of the money that they got approved as well, and it was a total non-issue in their rate case, whereas the utility before just said, we've got a lot of old stuff, we're going to start replacing it. It was disallowed 100%. Here they did a very reasoned, correct analysis, and it was approved without incident. It was a total non-issue. Last message is just engagement of regulators and commission staff. So ultimately, they're going to see this analysis. It's best for them to be comfortable, be familiar with it before you throw it on them in a rate case. And so if you haven't already, I would encourage you to talk to your commission staff. If you have an aging infrastructure problem, say things are getting older, we think it's increasing maintenance costs, we think it's not doing good things to reliability, we think it's just going to get worse, and we're going to start doing this type of an analysis, and we would like you to know we're doing it. And if you want to be involved or if you want periodic updates, then we're happy to do that for you. So this gives them familiarity with what you're doing. They can ask questions about the methodology, about the quality of the data. You can give them input onto you know, what their preferred scenarios or what approaches they're comfortable with. And then when you go into a rate case, you're likely going to have champions of what you're doing rather than skeptics of what you're doing. So it's not easy, but it can be done, and the case study shows that it can be done with effect. So that's what I wanted to present to you today. Thank you very much. And now we can open up it up for questions.
All right. Thank you, Richard. We have received some questions from our audience. And the first one comes in from John, and he asks, what other categories of equipment besides cable are utilities having aging infrastructure concerns with?
Yes, so that's a great question. And on the transmission side, you have steel lattice towers. And so you'll have transmission lines that are 40, 50, 60 years old, and these towers are starting to have a lot of rust and basically requiring a complete rebuild to address the aging infrastructure. And so that is one that some utilities are struggling with. On the distribution side, there's a lot of substation-related equipment that utilities are dealing with. old oil circuit breakers and substations would be one category, and then maybe a bigger one are large power transformers in substations. A lot of utilities, the average age of their substation transformers is over 40 years old. So those would be some examples of different categories of equipment that are aging and just can't be addressed in ways other than really a proactive aging infrastructure program.
All right, thank you. And our next question comes from Michael. He asks, does the population age based on failure assume that the cable is replaced instead of repaired?
So the population data is just based on what is in the ground. And so, for example, it's going to depend on the data systems that you have, but some utilities that I've had they know how much cable they have purchased and put in the ground, and then whenever they take cable out of the ground, they need to account for that in their accounting systems to adjust their rate base, and so you'll know how much you've actually taken out. And so it's a fairly accurate based on the initial amount that was installed and put in rate base minus what's been replaced. But yeah, this is based on you know, what you're adding in the ground, what you're installing, and then whenever you're doing some sort of a replacement or cutting out cable and splicing new cable in, how much you actually took out. So that's typically what I've seen at utilities. That doesn't, it's not related to failure rate at all. It's based on actual work orders.
Thank you. And our next question is, how would fiber optics change these models?
How would fiber optics change these models? I guess I am not sure. You can have fiber optics in cable, underground cable, for example, for temperature sensing. And so I'm not quite sure. I guess what you could do is if you had this type of technology where you have the locational temperature of cables that are buried, and if cables failed, you could look at historical data and try to look at, for example, if you had cable running next to a steam pipe and you had a hot spot in the cable, whether that would increase the failure rate of that cable or not. So you would have essentially ambient temperature conditions could be a function of failure rate. Cables that were in hot locations potentially would have different failure rate characteristics than cables that were in cooler locations, if I'm understanding the question correctly.
All right, thank you. We have another question coming in. They ask, what constitutes a failure of cable?
Oh, what constitutes a failure of cable? So this would be something that needed to be addressed. So of course, if you had a fault, that would be a failure. If you had a dig-in, that would be a failure. And I'll say that right now that non-age-related failures for all of these analysis were backed out. So if there was, say, a dig-in, that was not included in any of these failure rate models. So if you did have some sort of a fault, that would generally be what a failure would constitute. So this utility didn't do any like partial discharge testing or anything like that resulted in any replacement. So they were just faults that occurred on the cable system.
All right, thank you. And it looks like we have one more question we can do. What diagnostic test data did you factor in for your failure model?
No diagnostic test data at all. This was all just based on historical failure data. So they did not go and do any tan delta testing or any partial discharge testing, nothing like this. All just based on actual cable that failed in the field, that faulted in the field.
All right, thank you, Richard. It looks like we're at the end of the hour. Thank you so much for taking the time to speak with us today, and thanks to everyone for joining us. If we were unable to answer one of your questions today, we will make sure to reach out to you. To find more information and case studies regarding cable infrastructure programs, please visit our website, novitium.com. And we hope you enjoyed the presentation, and please take time to complete the survey at the end. We look forward to our next Masters of Reliability webinar. Thank you.